Welcome to the latest edition of You've Been Using These Two Words as synonyms your whole life, but they're actually two different things, and that is mass and weight. A lot of the time we think of them as exactly the same thing. They actually are not. I'm here to ruin all of that for you. So let's actually talk about what the difference between mass and weight is. Mass is just how much matter is in something. If I want something's mass, then I want how much matter is there. Okay, so it's also a measure of the inertia of the body. Basically, when something has more mass, it's more difficult to change its motion, right? If it has more mass, then you have to apply more force to get it to accelerate. So this is actually the thing that we measure in kilograms or pounds or something like that. That is your mass, but often we call that weight, Even if you want to figure out your mass, what do? You weigh yourself on a scale, but actually you're just finding your mass. You kind of are finding your weight, but what the scale's doing is it's taking your weight and it's actually doing a calculation to give you your mass. Because we're all on Earth, so it's going to be really easy for the scale to do that because it knows that gravity is pushing you down. And that's what has to do with weight. So weight is basically how much gravity is acting on your body. So weight is technically measured in newtons, okay? So it's basically saying, okay, how much mass do you have? And then due to that much mass, how much is gravity pushing down on you? And therefore, what is the force of gravity on you? So we know force or net force is usually some mass times acceleration. But in the case where we're talking about gravity, well, that has a very special acceleration, doesn't it? We know that has G, the gravitational acceleration of 9.81 meters per second. So, if you actually want to find your weight, you need to take your mass and multiply it by 9.81 meters per second squared. And that is your weight on Earth. So why is this important? Because when you go to somewhere like Mars, for example, you'll step on the scale and it'll say that you have less mass. You don't actually have less mass there, you just have less weight because gravity is no longer has the acceleration of 9.81 meters per second. It's about a third of that on Mars. So you step on a scale on Mars and the scale will read a third of what it does on Earth. You haven't lost any mass, but what you have lost is the amount of gravity that pushes down on you on Earth. So there you go. That is the difference between mass and weight. And so often we still say we're weighing ourselves when we step on a scale, or we're weighing something when we put it on a scale. But really, all that scale is doing is it's taking the weight that it feels, and then it's dividing it by 9.81 and giving you the mass. Because they're saying this is how much mass there is based on how much gravity is pushing this thing downwards. So there you go. Mass and weight, not the same thing. They're very much related, of course, but they're not the same thing. So happy to completely change your worldview. That's what I'm here for in physics. Okay, let's talk a little bit more about all these forces, because that's really what we're here for in the unit of dynamics. So before we go on to different types of forces, we're going to start drawing things called free body diagrams. So when we have more than one force at work, we need to start drawing diagrams to help us visualize what kind of forces are happening and what kind of forces are pushing things in different directions, okay? So that's what a free body diagram is. It's a diagram used to represent forces acting on a single object. So what you're going to do, you don't always have to draw the object, right? A lot of the time it's just like a box or a circle or something. And then you draw vector arrows on it. So what do the vector arrows indicate? Well, the force type, right? So you'll draw an arrow and then you'll put what kind of force it is next to it. It should be the direction. So for example, if we're drawing the force of gravity, it should be downwards towards the ground, right? And then of course the relative magnitude. So if one force is much bigger than the other, then the arrow should be drawn larger. Okay? All the different force types that you could be looking at. So this first one where you have to label the arrow with the force type, rather than having to actually write words, because why would we do that? We're physicists. I have a bunch of short ones for you where we have F and then we have a subtext that tells us what it is. So FG with that little subtext of G, that is force due to gravity, which is always downward. It's also known as your weight, okay? So FG and weight are synonymous. Those are two things you can always count on. There's something called a normal force. You're going to be like, what the heck is a normal force? I'm going to tell you. So it's always perpendicular to the surface. Is not always the force of gravity, okay? But basically, what is normal force? Well, it's the reason we don't just keep falling when we're on the ground, right? When we hit the ground, then we don't keep falling. We don't fall through the ground. Why not? Because there's still force of gravity pushing down on us. That's because there's something also pushing up on us at the same force as force of gravity. That's what we call the normal force, okay? So for example, it could be the force of the ground on you, pushing you back up, so you don't just like fall right through the floor, because that would be ridiculous and it would not be a very well built floor. So that is technically the normal force, is the force of the ground pushing back up on you. Okay, so Fn is your normal force. Make sure it's a capital N. That cannot be a lowercase n. So you do have to pay attention to the capitals and the lowercase. Fa is an applied force. So that's just when something's being pushed or pulled. Okay, so that's something is actually has a force being applied to it. F of F, this little lowercase f. So this is, again, where capitals and lowercase get really, really important. Okay, so capital S F always means force. Lowercase f here now means friction. Okay, so this is force of friction. So this is always going to oppose motion. So, of course, friction is why things in our universe don't just keep going. They don't always follow the law of inertia. Well, they do, but the outside force that a lot of things are being acted upon by is friction. It's what slows us down. It's a heat that's created between two surfaces when they rub together, right? And then Ft with the capital T there, that is force of tension. So that's when something's being pulled by a rope or a chain or something like that. Then there's a tension force in the rope, and that is pulling the object. Okay? And finally, one that we don't actually use in Physics 20, but that's the force of compression. Okay? So if something's being compressed, something's being stretched like a spring, we're also going to call that spring force in our final unit. So look forward to that, but we don't use that one as much. These guys are the ones that you really got to know for now. Okay? So, for example, let's just draw a few free body diagrams so you get an idea of what's going on. So a box is at rest on a rough incline. What does that mean, rough? That just means it's telling you that there's friction, right? Because if it's a rough surface, we know that there's definitely going to be friction. If it's a really, really smooth surface, if it's something like ice, then sometimes we assume that there's no friction or very, very little friction. But rough just means, oh, it's a really rough surface, so something's going to stop on it. Okay, so that means there's friction. Okay, so I want to draw a free body diagram. So if it's on an incline, what does that mean? It means that, there you go, there's an incline and there's going to be some angle there that the incline is on. So it's a box. Oh, that's so nice and easy to draw. Let's draw a box here. It's just at rest on the incline. Okay, so what does at rest mean? Well, it just means that all your forces need to be balanced, okay? If your net force is 0, then it's not accelerating. So that's just something I'm going to pay attention to. Now, what's tough about an incline? So we have force of gravity for sure. Force of gravity is always pulling something down. But when it's on an incline, force of gravity isn't going to be like, oh, I'm going to be really nice and just like go along with the incline. Nuh-uh. Force of gravity pulls you straight down towards the ground all the time. So here, my force of gravity is actually pulling it straight down. So I'm going to do that, and then I'm going to put Fg right beside there. Okay? So that's my force of gravity. I'm actually going to move that to the other side. You'll see why in a minute. Okay, what other forces do we have? Let's go back to our list. So for Fg, we have normal force, perpendicular to the surface. So there's not always a normal force. There's only a normal force when it's on a surface. Is this box sitting on a surface? Of course it is. So it's got to be perpendicular to the surface, so it's not actually going to be strictly opposite Fg. It's going to be kind of like that, because it's got to be perpendicular to this surface. Remember, perpendicular means it needs to make a right angle to it. Okay, and then beside it, I'm going to put F and then a little N down there to say that that's normal force. Okay, so what other forces are at work? Well, rough incline, I already said that usually means force of friction, and the force of friction always opposes motion. The only problem is it's at rest. It's not motioning. It's not going anywhere. But think about, where would it usually be going if it was moving? It would probably be going downwards, right? Down the incline. That makes the most sense because, well, gravity is pulling it down. So therefore, my force of friction is going to be opposing that. So it's going to be something like that. Okay? Now, something we're not going to get into for another couple lessons, but I still want to talk about, is this Fg. So this is kind of weird, where we have stuff kind of in this plane and this plane, but then we have this weird thing going downwards. Okay? So this is what we're going to do in inclines, is we're going to start making things a little bit different. And what we need to do, because we always need to have an XY plane. We always need to have our X direction and our Y direction. So the thing here is, I don't like this Fg, because I like things to be parallel to the surface or perpendicular to the surface, not whatever Fg is. But the thing is, I can break Fg up into the perpendicular and parallel surfaces, right? I can kind of draw the vector diagram where Fg is the resultant vector, right? And it'll look something like that, because Fg is pulling it downwards perpendicular to the surface and down the incline parallel to the incline. Okay? So in the future, we're going to call this FGY and FGX. Reason being is because I'm going to make this into my new x-axis and this into my new y-axis. Okay? We are going to get into that more when we do friction on an incline. All I want you to know here and note here is how to draw a free body diagram, and that is a free body diagram. So we don't always draw the surface on the free body diagram, but that is one where I had to, because we're on an incline, so it just helps. Okay, but you see, it's an object. It has a bunch of arrows coming out of it telling me where the forces are going, and they're approximate magnitude, right? So the FF here is pretty much equal and opposite to the FGX here, because we know they should be equal and opposite, because they should be a net force of 0 since it's not moving. We see that Fn and Fgy are about equal and opposite, because they always should be, because it's not moving up or down, right? So we know when we have something not moving, my net force should be 0, so my arrows should be roughly the same size. Okay, let's do another free body diagram. So a curling rock is sliding across the ice and comes to a stop. This is something I can draw. I can draw a curling rock. So I'm going to. So just stick with me for a minute while I draw a curling rock. Look at that beautiful curling rock. Isn't that great? Usually you do not have to draw the object, but I just do with this one because I'm like, that's something that's easy enough to draw. I can do that. So there you go. There's my pretty curling rock. From now on, you will only be seeing me draw like a circle or a box or something, because who actually has time to do this every time? Come on. So a curling rock is sliding right across the ice and comes to a stop. Okay, so it's sliding right, but it doesn't say that it's actually being pushed right. So that's really, really important to note. So we know that its velocity is going this way to the right, but it's really important to note that it's not actually being pushed to the right. It was pushed to the right at some point, obviously, but it seems from here that it's actually being let go. Okay, so it's really important to note that. And then it's coming to a stop. Why is it coming to a stop? Because there's still friction on ice. There's a lot less, but there still is friction on ice. So that means friction is working against the motion and bringing it to a stop. So what we can say here is our friction is actually going against the motion, because that's what friction always does. It goes against the motion and it's bringing it to a stop. But since it doesn't say it's being pushed in the right direction, then I cannot draw an arrow to the right because there is no applied force to the right. Okay? There are two other forces at work. Always force of gravity, because we're going to assume we're always on Earth. So there's a force of gravity going downwards, Fg. And then, of course, it's on a surface and it's not moving up or down. So we need a normal force going upwards, and it should be about equal and opposite to Fg. So there we go. There's a free body diagram for this situation. Okay? Let's try one more. So we have a fish hooked on a line and is lifted out of the water vertically at, well, one we have constant speed and one we have an acceleration of 2 meters per second, I'm guessing upwards. Now, why is this special? Now, I'm not going to draw a fish. So here, this is the point where my drawing skills are done. Okay, so I'm just going to draw a box because that's just basically what we draw for everything in physics. So constant speed, what does that mean? When something's going at a constant speed, that means there's no acceleration. Why is that important? Remember, force is equal to mass times acceleration, or at least net force is equal to mass times acceleration. So if my acceleration is 0, guess what my force is? It's also 0, right? Doesn't matter what the mass of the fish is, it's 0, right? So the net force needs to be 0. So that's why it's so important, okay? So the fish is hooked on the line, is being lifted out of the water. So what's it being lifted out of the water with? A fishing line. So that's like a rope, basically, right? So that's actually force of tension. So keep in mind, this fish is no longer on a surface. It's not resting on a surface. So there's no normal force. What do we call the thing that if it's being like pulled by a rope? Oh, there it is, Ft, force of tension. So this is actually force of tension going upwards. There we go. And then what else is at work here? We just know that then obviously force of gravity must be going downwards. But because my net force is 0, guess what? These arrows should be equal and opposite. And of course, I don't need you to take out a ruler and make sure they're perfect, but they should be look almost the same length. Okay, so that's really important. Now we have an acceleration of 2 meters per second squared. And I'm guessing it's acceleration up because it is moving upwards, right? So what does that mean? It means now the force of tension should be not equal and opposite of Fg. It should be still opposite, but it'll probably be larger since this thing is accelerating upwards. Okay? So if I look at the fish, in quotation marks, I'm making air quotes, but you guys can't see it. If that's my force of tension, I know my force of gravity should not be as large as that. So it should be drawn so it's less, okay? And that's the biggest difference between these two things. It just means then when it's accelerating upwards, the upwards force better be the bigger force. Okay? And it's really important for you to draw it like that. So in this case, we know my force of tension is greater than my force of gravity because it's overcoming it to make it accelerate upwards. Okay? So it's really important that you know if there's acceleration or not. If there's no acceleration, equal and opposite. Okay? So Ft here equals Fg. They're just opposite signs, right? We'd make Fg negative and Ft positive. But when there is acceleration, one of them needs to be bigger, and it'll be in whatever direction that the acceleration is. Okay? So that's really, really important to note. So with this in mind, I want to do a few net force examples using free body diagrams to show us how we're going to add our net force. Because remember, net force is just the sum of all the different forces at work. Okay? So, if you have a net force question where you have to figure out the net force of all these and then use mass and acceleration and all that fun stuff, what are you going to do? First, you're always going to draw a free body diagram. Oh my goodness, please. Okay? It's actually going to become a mark on your tests and quizzes now. So please draw your free body diagrams. Then you're going to apply Newton's second law in either or both x and y directions. Sometimes, like in the scenario we just had, we only had the y direction. So why do I even care what's going on in the x direction? There's no forces in the x direction, so I'm only going to look at the y. But some of them, then I need to look at both. Okay? So make sure you separate them though. There's going to be the net force in the x direction, the net force in the y direction, and you are going to treat them separately. Okay? And make sure you always choose your positive direction to match the direction of acceleration. Oh my goodness, you guys, this is so important. Okay? If something's accelerating upwards needs to be your positive direction. If something is accelerating downwards, you must make downwards your positive direction. Okay? In kinematics, you're kind of allowed to choose a little bit. Now you can't. Okay? Wherever your acceleration is going, that's your positive direction. And then you're going to use the diagram to replace your net forces with your individual forces, okay? So what does that mean? Let's just do an example. It's going to help a lot, and then we'll go back to the solving steps, and you'll be like, oh, okay. So we have two students pulling a box horizontally to the right. Oh, I love directions. With a force of 20 newtons each, okay? So we have the force of friction on the 40 kilogram object is 10 newtons. We want to determine the acceleration. Okay, first step, always draw a free body diagram. Okay, so again, they're actually just pulling a box, so I don't actually need to simplify this drawing because it's just a box. So what does that mean? So two students are pulling horizontally to the right. So I need two forces going to the right. Yes? Okay, so those are both applied forces, so we'll call this FA1 and FA2. How about that? Okay, and then we have a force of friction, so that those two forces are 20, and my force of friction is 10. So the force of friction arrow should be approximately half. Okay, of course, I'm not getting out a ruler to look at, to measure anything, but it should look about half. Okay. The biggest problem is if they look the same length or force of friction looks bigger, then I'm going to clock you for that, okay? There's two other forces at work that a lot of people are like, but I just should draw the forces I care about. No, draw all the forces. It's a free body diagram. Free body diagram automatically means I want to know all the forces at work. This thing I'm assuming is happening on Earth because I don't think I have any students that are astronauts at this point, but you never know. So there is a force of gravity, of course, going downwards, and that means, and it's also on a surface, we're assuming, right? Because it doesn't say that anybody's carrying it. So I'm going to assume there's a normal force that's equal and opposite. Okay, so there we go. There's my normal force. And there is my free body diagram, right? There's the object and all the forces that apply to it. Remember, the arrow should always be pointing away in the direction that they're actually going. Okay, so I want to know the acceleration. How do I know that? Well, I know, of course, net force is equal to mass times acceleration, so I'm probably going to do that. And what is net force? It's the sum of all the forces. Okay, it's probably going to be accelerating to the right because there's more force to the right. There's two people pulling it, and then friction is opposite. So I'm going to go ahead and say right is positive. Okay, so what do I have? In the going right, I have the two applied forces. So I'm actually just going to be looking at the x direction here. I probably don't care about the y direction because there's no acceleration in the y direction. I just have to draw those arrows, but nothing's happening in the y direction. I don't care. So I'm just going to ignore it. Okay? So I know my first applied force is going to the right. I know my second applied force is going to the right, so I'm going to add it. And then I know my force of friction is going to the left, so I'm going to subtract it. That's net force, you guys. It's the sum of all the forces, but make sure you put in a minus when something's going the opposite direction. So that's my net force in the x direction. Okay, you can't pick and choose. You need all the forces that are at work in the x direction. And I have those now. And that is equal to mass times acceleration. Okay? Easy peasy. If I want acceleration, I just take this and divide it by mass. Okay? So let's do that. Remember, the applied forces by each student were 20 newtons. So I'm going to add 20 newtons to 20 newtons. And then the force of friction was 10 newtons. So I'm going to do that. And then mass was, 40 kilograms. Give you that as well. So there we go. So 20 plus 20 is 40 minus 10 is 30. 30 divided by 40 is 3/4, which is also 0.75. Okay. How many significant digits do I need? 2, 2, and 2. So it looks like I need 2. So 0.75. Remember that 0 is not significant because it's a leading 0. So that is a 2 significant digit answer. Perfect. And we're done. Okay, so remember, those y directions need to be drawn on your free body diagram. But if you don't need to use them, don't use them. Because sometimes it's like, who cares? Like, great, thanks for helping me draw a free body diagram. But they had nothing to do with the acceleration of the object. What's accelerating the object? The two students pulling it. Okay? So just make sure that you only use the stuff that is applicable. Let's do one more. We have a fish accelerating out of the water at 2 meters per second. 2 meters per second squared. This looks like this one, right? So that means I already know what this free body diagram looks like, right? Because it was that one where it's accelerating upwards, so I knew that my force of tension was bigger than my force of gravity. So we just make sure that we draw it like that, where the force of tension is clearly larger. Okay, so we have the acceleration. The maximum tension in the line is 65 newtons. So that's basically how much tension it can take. So what can we say about the mass of the fish? So basically, if the maximum tension that the line can take is 65 newtons, I need to know the mass that goes along with that. And that would be the maximum mass of fish that I could catch. Well, let's face it, you could catch, because I'm not a fisher, without the line breaking. Okay? So again, I'm dealing with mass, acceleration, and forces that are going on. So let's figure out how to do this. So we know our net force is always equal to mass times acceleration. I'm going to make the direction of acceleration positive, so it's accelerating upwards out of the water. Okay, and what is my net force? Well, the tension force is the positive, and the gravitational force is the negative, so I'm going to minus that. Okay? So here's the other problem. We were not given gravitational force, but we know how to find it. Remember, that's mass times gravitational acceleration. So that's what we're going to do. That's actually mass times gravitational acceleration. Now remember, this g right here is a subscript. This g is not a subscript. So do not treat it as such. That is the mass times 9.81, okay? Or negative 9.81. Actually, it's just 9.81 here. I already accounted for the negative by subtracting it. Okay, so now we have to solve for mass. Problem, mass is in 2 places. How the heck are we going to do this? Well, the good news is we had that one kinematics equation that had t and t squared, and I said never use that to solve for time unless you want to use the quadratic equation. This is different. Neither one of the m's are squared, so it actually makes it a bit easier. And you guys know how to do this, but I'm just going to maybe remind you how you would do this, but you have learned it in your math classes, absolutely. So I'm going to add the mg to both sides so I can get all my m's over to one side of the equal sign. That's the first thing I need. The second thing I can do then is substitute out an m because both terms here have a factor of m. What does that mean? If I factor out an m, I have a plus g left, okay? Because I took the m out of both things. So remember, these two things are equivalent. I didn't actually change anything. I just wrote it in a different way, okay? And now, now I can go ahead and divide both sides by a plus g to get m all by itself. Because since I'm multiplying m by a plus g is like an entire thing, I can divide the whole side by a plus g. Okay? And that is how you solve for that. So there's your little reminder and something you can do going forward. So, my mass. How do I find that? Well, it's the force of tension divided by the acceleration plus the gravitational acceleration. I'm going to go up here because I'm running out of room. Okay, so that force of tension was given to us at 65 newtons. Okay, and then A was 2.0 meters per second squared plus G is 9.81. Now, here's a really, really important thing, and I get it. It's going to mess you up. You're going to want to put negative 9.81 there, and I 1,000% get why. The reason you don't is because we actually already accounted for the fact that it's negative right there. Okay, so just think about that for a minute, wrap your head around it. It's okay if it's a little bit weird at first because it's so counterintuitive. You're like, I said upwards is positive. Why am I making 9.81 negative? The reason because you're not doing it here is because you already did it here. And so if you make it a negative again, you're really just undoing what you already did. And then actually that's wrong. So that's why we're putting in positive 9.81, which I know feels crazy counterintuitive to you guys. Okay, when you calculate this, you get 5.5 kilograms. There we go. So again, the question actually says, what can we say about the mass of the fish? Well, basically, since this is the maximum tension, this has to be the maximum mass. So we can say that you can catch any fish that's 5.5 kilograms or less, okay? As soon as they try to catch a fish that's greater than 5.5 kilograms, that fish line will snap, okay? Because the maximum tension in the line is 65 newtons. So if they catch a bigger fish, they got to get a better line. And that's that. Okay, so you guys, that's how you solve questions with free body diagrams. So remember, here are your steps. You draw the free body diagram first. You apply Newton's second law in either or both x and y directions. In both of our equations or both of our examples, we only had to choose one direction, right? Choose the positive direction to match the acceleration, really, really important. And then we chose the diagram, or we used the diagram, and we replaced the sum of forces with like the actual individual forces that were at work, right? We actually summed all the forces that were at work, which is why the free body diagram is so important, because it helps you organize all that information. Okay, there you go, you guys. Good luck.